Hello, I'm George Farquar, and today I'll be talking about DNATrax, DNA tagged reagents for aerosol experiments. This is a material that we've developed at Lawrence Livermore National Laboratory that will revolutionize aerosol transport studies. What is DNATrax and what is the need? First of all, aerosols are suspensions of fine solids or liquids in a gas. And aerosols have many applications to be studied, such as biosecurity, to track indoor airborne contaminants, environmental health, and health and human effects. And DNATrax is a material that we will use for those particular studies. And what is DNATrax? DNATrax is a two-component system. It contains a DNA barcode. So the barcode is made out of non-biological DNA that we can place into every one of the particles that we make. And that barcode allows us to identify the material later on when the material is collected. And each barcode is encapsulated in a small droplet of sugar material, and we're using an FDA-approved maltodextrin powder right now. And that has a huge advantage over other materials because it is approved for human consumption, so there's very low regulatory burden for us to receive approval for releasing this material. So what we get by combining these two materials, our unique barcode and our FDA-approved sugar, is an inert, non-living, non-viable, non-infectious material that we can get approval for release for aerosol transport. With 100 bases of DNA in each particle, we have about 10 to the 60th possible barcodes, so we can make a virtually unlimited number of barcodes and allowing us for multiple releases without decon. As you can see, to the right-hand side of the screen is a schematic or cartoon of what the particle looks like. The blue would be the maltodextrin, or the sugar particle, with a single or multiple copies of DNA in each side to act as the barcode. As you can see in this photo here, there's an aerosol release being conducted at the Pentagon. To the left is a black box. It's an eductor that is a dry aerosol powder dispersion device. And coming out of the front of the nozzle is the DNATrax material being blown down one of the hallways in the Pentagon. This is our first successful test and our first test at the Pentagon. And the quote at the bottom, "As a result of the support received from the Defense Threat Reduction Agency and Lawrence Livermore National Laboratory as part of this testing, Pentagon Force Protection Agency has been able to make marked performance improvements to the Pentagon's biological detection systems." Now, this came from the Deputy Director of the Pentagon Force Protection Agency. And as the scientist developing this material, it's very significant. Our only goals for this test was to show that it transported appropriately, we were able to release it and collect the material. But beyond our goals for the test, we were also, on our very first test, able to make marked improvements to their detection system. So it was not only validated as a possible simulant for improving the systems, we made improvements to their systems from day one. So as mentioned in the previous slide, this material has been tested at the Pentagon. Two tests have been conducted, November 2012 and February 2013. The primary objective was to determine the suitability of the simulant as a tool for validation testing of aerosol systems. 4 releases occurred, evaluating the initial concept and the simultaneous release. The PIFPA sensors were triggered. That includes, as shown on the bottom, the dry filter units, which is a filter collection system, and later we did PCR analysis on the resulting material, and their handheld particle counters, and additionally aerosol particle sizers that are shown at the bottom. PIFPA models were evaluated and compared to the experimental data and given a real-world challenge to understand how that can occur. So the DNATrax has quite a few competitive advantages over more traditional methods. Before DNATrax was developed, materials such as traditional spores were used for aerosol transport studies. They had the drawback of needing cleanup after use, single release, and real difficulty in obtaining approval for release in an environment that was populated and for health concerns. DNATrax eliminates those. It's safe, it's made with an FDA-approved sugar, so we've had very little, if any, difficulty at all receiving approval to do releases. And we've been approved to do releases both at Lawrence Livermore and at the Pentagon to date. And you can do multiple releases at the same time. And this is probably one of the most significant advantages of DNATrax. You can take 2 materials or 2 sets of DNATrax with different barcodes and do simultaneous releases from different places in the facility, collect that material after it's transported through the facility, and deconvolute where the particle is transported to. Using traditional spores, you would be required to do a single release, decon the facility, which can take 1 to several days, and then do a second release to determine that. With DNATrax, that's completely limited by using the barcodes to identify where the material came from. Post-testing cleanup is minimal if required at all. There's a low burden for approval, as I've mentioned before. We've had no problem whatsoever receiving approval to spray powdered sugar with non-biological DNA. And we can tune the particle size to match the industrial need of that particular application. DNA barcoded spores are another potential competitor, and barcoded spores have some of the same advantages of DNATrax in the sense that they are barcoded, but they're genetically modified, and to receive regulatory approval to release a genetically modified organism will be extremely difficult to do, and that will add greatly to the expense of using that material as it's developed. And of course, there's also tracer gases which can be used for aerosol transport, but once again, only one release can be done at a time, and they have vastly different properties than aerosols or 1 to 10 micron sized particles. But the advantages of DNATrax over other materials led to the prestigious award of the R&D 100 this year, and that occurred last month. For more information, please contact Catherine Elizondo at Lawrence Livermore National Laboratory in the Industrial Partnerships Office.